Public presentations of humanoid robots, like the Tesla bot, suggest that machines have already mastered the complexities of the physical world. We see them sorting objects by color or maintaining a yoga pose with human-like balance. But industry experts have raised questions about how autonomous these machines actually are. In many viral demonstrations, the robots are actually controlled via teleoperation, where a human operator guides the machine's limbs from behind the scenes to perform the task. While digital AI can predict the next word in a sentence with high accuracy, the physical world is less forgiving. A robot cannot guess how to navigate a snowdrift or handle a fragile egg. It requires a precise understanding of gravity, friction, and material resistance that text-based models simply lack. Engineering a mechanical body is a solved problem. The current bottleneck in the robotics industry is data, the massive amount of physical training information required to move a robot from human control to true autonomy. By 2026, the industry entered a phase called AI takeoff. This marks the transition to agentic AI, systems that no longer just analyze data on a screen, but can independently plan and execute complex physical actions. To acquire the data needed for this shift, developers are building high-fidelity digital universes. These simulations generate synthetic data, allowing AI brains to practice movements millions of times without the limitations of real-world time or safety risks. This shift is driving a massive investment in computing power, with cloud providers projected to spend $600 billion on infrastructure in 2026 alone. Computing capacity has become a primary strategic asset that nations are struggling to secure. To support these workloads, the industry is building AI factories. These massive data centers are handling a surge in demand, with orders for specialized AI infrastructure reaching $1 trillion through 2027. The hardware driving this scale is the Nvidia Blackwell architecture. These GPUs are built using a custom 4-nanometer process and contain 208 billion transistors, allowing them to handle the massive mathematical loads required for agentic reasoning. Using 5th-generation NVLink technology, up to 576 GPUs connect into a unified computing domain, functioning as a single, massive processor. This bandwidth allows agentic AI to process trillion-parameter models with minimal latency, providing the speed to reason through complex environments in real time. This concentration of power creates extreme heat. To keep these systems stable, data center designs have shifted to rack-scale liquid cooling, using intricate thermal management hardware to keep the processors within safe operating temperatures. To manage these clusters, developers use OpenClaw, an operating system built specifically for agentic computing. It provides the software layer needed for autonomous agents to run 24/7 with persistent memory and real-time planning capabilities. This combination of specialized hardware and software creates a complete AI factory, a facility designed to house and power the next generation of digital workers. Real-world testing is slow and expensive. If a robot fails during training, it can damage its chassis or its environment, making it nearly impossible to scale the learning process safely. Instead, robots are trained using the Newton physics engine and Cosmos world models. These systems create physically accurate digital twins, where a robot can fail and reset thousands of times a second. The Newton engine ensures that every digital interaction adheres to the laws of physics. It mimics real-world gravity, surface friction, and material properties, so the robot learns how objects actually behave. Robot foundation models like Isaac GR00T spend millions of hours in these simulations. They refine their physical policies, the rules governing how they move, until they can navigate complex environments with high reliability. Once the AI brain has mastered the task in simulation, it is downloaded into a physical industrial chassis. Because the digital twin was physically accurate, the robot can transition to the real factory floor and work with high precision on day one. High-fidelity simulation bridges the trust gap. It allows companies to deploy autonomous machines with the confidence that they will behave safely in the physical world. We are moving toward a period of shadow autonomy. In this environment, AI agents manage physical workflows and digital systems with minimal human oversight, operating at speeds that exceed human reaction times. This lack of visibility into AI decision-making is a national security concern. Hostile actors have already demonstrated the ability to use AI agents to automate 90% of a cyber attack, bypassing traditional security teams. Because of these risks, compute power has become a critical strategic asset. Dominance in AI infrastructure translates directly to a nation's ability to defend its networks and maintain industrial productivity. This has created an intense geopolitical contest. The United States and China are competing to lead in international AI markets, using export controls and standard-setting bodies to dictate how and where these machines are deployed. The winner of this race will control the future of global supply chains and defense capabilities. Success in physical AI defines which nations will hold economic supremacy in an automated world. Public attention often settles on the bipedal robots that mimic the human form. However, these machines are only the surface of the revolution. The real transformation is happening inside massive, climate-controlled server farms. Here, trillions of calculations are executed every second to simulate the physical universe and teach machines how to navigate our reality. To teach machines how to work in our world, we first had to recreate that world perfectly inside of a computer. That boundary collapsed in 2026 with the deployment of agentic operating systems. Software frameworks like OpenClaw allowed intelligence to break free from the prompt and response cycle, operating without waiting for human keystrokes. These models began executing continuous, autonomous loops. They could plan a multi-step project, rapidly execute new code, and correct their own errors, becoming relentless digital workers. Maintaining an intelligence that thinks constantly, juggling thousands of concurrent threads without pausing, requires a scale of raw physical power that traditional data centers simply cannot provide. The server racks used to host websites were insufficient for this load. The industry pivoted to constructing specialized facilities known as AI factories. This shift represents a $1 trillion global investment in computational power through 2027. The silicon heartbeat of this expansion is the Vera Rubin supercomputer architecture, a vertically integrated system designed specifically for agentic workloads. These systems operate at continuous exaflop speeds, performing 1 quintillion calculations every second. By combining this processor architecture with thousands of interconnected nodes, engineers generated the computational density required for real-time robotic reasoning. The hardware now processes millions of real-world variables, including spatial geometry, weight distribution, and friction, simultaneously and in real time. This raw compute provided the engine the intelligence needed to exit the digital world and enter the physical one. While the digital brain evolved, the physical bodies available to it remained limited. For centuries, mechanical robotics relied on the rigid, pre-programmed movements of gears and pulleys. Engineers cannot simply write a line of code to explain abstract physical concepts like dynamic balance or the exact pull of gravity. This simulation occurs in the omniverse, a world operating with mathematically perfect physical laws. Inside this simulation, differentiable physics allow the AI to calculate the mechanics of motion directly within its neural network during training. Millions of phantom robots are run through these parallel simulations concurrently. They fall, drop objects, and collide with obstacles, immediately self-correcting their parameters at the speed of light without ever bending a piece of real metal. Foundation models like GROOT use this data to autonomously reason through the mechanics of motion rather than following human-written scripts. Prior to downloading into a physical frame, the intelligence has lived thousands of lifetimes of trial and error in a matter of months. This accelerated digital evolution finally bridged the gap between software and kinetic action. Eventually, the simulated intelligence transfers from the digital ether into physical steel, synthetic actuators, and precision optical sensors. In 2026, this technology has reached mass production, with advanced humanoid robots designed for general-purpose tasks. Heavy industry has already integrated these machines, with Hexagon AEON robots working synchronized 10-hour shifts on automotive factory floors. These entities can look at a novel object, understand its geometry, and manipulate it with precision, without any pre-programming. In 2026, the cost and capability of these machines have converged, enabling a shift in physical labor that mirrors the earlier explosion of generative text. The glowing screen is no longer the boundary of AI. We have now engineered a reality where autonomous, kinetic intelligence physically manipulates the very atoms of our world.